All right. So we're here, this is the cryptography class, and this is the last lecture. And I wouldn't even have a lecture on the last day normally, but the remaining topic was TLS, which is really important. So I do want to present that, and then I'll just be around to answer any questions anybody has. So let me get my TLS up, which is going to be one of these. All right. Yeah, that'll do. Okay. Hey, you know, I could, maybe I could be really cool. I heard somebody complaining about this. Maybe I can do it without, don't know if it's any better. Anyway, so, I think it's better the other way, because my slides are not quite the right shape. Anyway, so, we'll talk about what the requirements for TLS, the protocol suite, why 1.3 exists, and I see the Humble Bundle. Yeah, there's that Humble Bundle that some people might like. Yeah, and usual thing, the strengths of it and how it can go wrong. So TLS has been around for a long time, invented by Netscape in its earlier version SSL, and this is what added a layer of encryption to internet traffic. Originally, there was no layer of encryption, and of course that's terrible. People were logging in on plain text on HTTP and FTP, and that's why, you know, while that was still happening, people might want VPNs. Yeah, and by the way, quite a few of those books on the Humble Bundle are available for free on the internet too, and most of my textbooks are. Anyway, so TLS can now handle any kind of content, but there were a lot of attacks. TLS is really important. It's protecting everybody's traffic, and so a lot of people attacked it, and they found many flaws with names like Heartbleed and Beast and Crime and Poodle. And TLS 1.3 was the latest update, which completely overhauled the protocol and really cleaned it up. It removed the old algorithms that weren't safe and removed unnecessary features that made trouble. Yeah. All right. So it's giving you a secure channel, and it prevents man-in-the-middle attacks. Now, in principle, there is no way to stop a man-in-the-middle attack with just two parties. You have you trying to contact a server, and how do you know if you really contacted the server? The only way to really know is to have some trusted third party that vouches for them. And so you have to have certificate authorities, which is the trusted third party. So here's the requirements to do this. It has to be efficient. It can't be too much CPU. It has to work on any hardware. It has to be extensible and versatile to be functional, to protect the internet traffic, which is so varied and constantly changing. So this is the TLS protocol suite. Now remember, your OSI model is here, and the first four layers really are distinct and have different addresses, and 5, 6, and 7 are pretty much all blended together and in your browser and your email client. But TLS is above the transport layer, adding security to it. And you can run over TCP or UDP. The only kind people normally talk about is the TCP layer, but there is a UDP version called DTLS. So, it started in '95 from Netscape. They made SSL to encrypt network traffic so you could log in, and that was SSL. Would you call TLS at layer 5? Yeah, I don't know. I don't know where you'd put it in, but somewhere above 4 is where you'd put it. And I think there's no real clear reason to put it anywhere in particular up there. Just sort of a philosophical argument. Like I said, the layers above then don't really have a real clear distinction. Anyway, all the versions of SSL are now no longer, they're too old, they're too used things that aren't trustworthy anymore. Nobody should be using any SSL at all. TLS was the upgrade from '99, and all the TLSs are pretty good, but 1.0 and 1.1 are the oldest and weakest, of course. Every version keeps getting better. Yeah, you could say secure. You could put it at layer 5. You could argue for that, but I think it's really just a philosophical argument of no real meaning. Anyway, so TLS 1.2 is again better, but it had some vulnerable things like AES CBC, which we've been attacking and padding oracles, and it carried along through a lot of old things for backward compatibility. So 1.3 was the next step forward. Now, by the way, I think 1.2 was largely motivated by Edward Snowden. Edward Snowden revealed that the NSA had been archiving vast amounts of data waiting to decrypt it later when they managed to impound one of the servers. And everybody wanted to upgrade to, I think, 1.2 to get forward secrecy. I think that was not in 1.1. Oh, no, I think O'Reilly's legal. Or the O'Reilly, when you get those free things from City College, I think you're actually getting them from the City College library or something. Anyway, all right. So you've got data encapsulation and you have key agreement. These are the issues. You have to have some kind of encryption here, and you have to have some way to establish the key, which turns out to be the difficult and weak spot, as you might imagine. So here's how TLS looks like. You send a SYN/ACK just to open a TCP communication on a port with no encryption at all. And now the client sends a client hello saying, I want a TLS connection. The server sends a servlet hello, which lists the possible encryption routines. The client chooses one of them and then sends a reply, and the server sends another reply, and that's the 7-way handshake to make TLS. And not shown here is the client takes the certificate it got here and verifies it with a third party. So the client hello lists the ciphers available. The server says, I can pick any of these 10 encryption protocols, and the client decides which one it can handle, because the client might be an old browser or a weak device or an IoT device or any weird thing that can't really do all the fancy stuff. So here's the client hello. And here's one I captured showing all these encryption routines. TLS of elliptic, you should know all these terms by now. AES 128 with Galois counter mode, Galois counter mode or something, SHA 256, cha-cha-cha, elliptic curve digital signature algorithm, elliptic curve Diffie-Hellman, ephemeral key, and so on. All the protocols we've been learning about are all here in various combinations. All right, and there's the server hello, where it's picked one, change cybersec protocol. You switch to this one, and now you're ready to go. And all right, so the client generates a key pair, then sends a client hello with the cipher supported and public key of C. The server generates a key pair, computes a secret, derives keys. So you make a secret, which is Diffie-Hellman. Remember, the Diffie-Hellman is a number that's not necessarily really evenly distributed or the right length to be a key. It's more like a password, so then you use a key derivation function to make a key out of it. Now you're ready. Then the server replies with a certificate and a signature and a MAC to verify it. The client verifies all these things and then verifies the certificate with a third party, and then it's willing to believe the key that it derives from the shared secret, and now they can communicate with AES now that they have a shared secret key. That's how it works. Now you have to trust the third party. The certificate authenticates the server, and you have to check with the third-party certificate authorities, so you have to trust those certificate authorities, and they're hard-coded into your browser, and they're hard-coded into your operating system, the standard list. So the certificate looks like this. There's a Cloudflare certificate, and it's got fingerprints, and it tells you where it came from, DigiCert, so you can check your hard-coded address for DigiCert and see if they say that's good. There's a certificate chain going up the hierarchies. Here's Cloudflare. Their signature proves that they really came from these guys, and these guys are an intermediate one, and their certificate is signed by these guys, who should be found in your list of trusted root certificates, or your browser is going to warn you that this certificate is not trusted. It does not have a chain leading back to a known trusted root of trust. All right. And what's kind of funny is Internet Explorer 3 or 4 did not do this. So you could just give them a fake certificate and run your own server one step up, and it would not do the other steps. So you could, anything that can go wrong will go wrong. Anyway, so here's the TLS record. You've got the type of data transmitted and then some patterns, code numbers here, the usual stuff. You have to pad it with zeros. You don't want short messages. You don't want the encrypted versions of them to be shorter, so you know they were short, so you pad them to 0 to prevent traffic analysis, where you just deduce the contents from message size. That's why you also don't allow compression of the stuff anymore, because then that would give you a clue from the size about the content. So There's authenticated encryption. We talked about a key derivation function and a Diffie-Hellman operation. All the things we've been through. So TLS 1.3 is very simple. All it lets you use is AES in Galois counter mode in something related called CCM, or using the Cha-Cha-20 stream cipher. It doesn't let you use AES with CBC or with textbook mode, electronic codebook mode, or any of the foolish modes. It only lets you use ciphers that are much stronger, that don't have the major defects the earlier ones did. And you can be 128 or 256 bits, but nothing lower. Older versions would let you use 64-bit or 80-bit keys, and those are gone in TLS 1.3. So the key derivation function is an HMAC using SHA-256 or SHA-384, which is fine. And you have Diffie-Hellman. You got two choices. You can do elliptic curve, or you can do the prime number based Diffie-Hellman. If you do the elliptic curve, you have 3 of the NIST curves, or you can use the 2 most famous curves that are not NIST curves, 25519 or 448. So that's it. You have 5 choices, but they're all good choices. And if you want to do the traditional prime number Diffie-Hellman, you got 2048 to 8192. And that's possibly a weak spot. 2048 is short enough that it's not really recommended anymore. But it is provided in TLS 1.3. All right. And so here's the improvements. They removed all these old weak algorithms, like SHA-1, RC4, MD5. A whole bunch of old things that we've been through in the earlier chapters have all been removed. It's removed just features that were dangerous. Like I mentioned, there used to be data compression options, but data compression will change the size of the packet depending on the contents, and therefore leak information about the contents. And so they got rid of that. All right, now it's got downgrade protection, single round-trip handshake, and session resumption. So the downgrade attack goes like this. The client is trying to get to this server. They want TLS 1.3. You intercept the traffic and say, send her TLS 1.1 instead. And then he sends a server hello for TLS 1.1. That's a downgrade attack. And this works in many, many systems, not just TLS. You can do it to domain controllers too, to make them think you're using an old domain controller and stuff like that. If the protocol doesn't prevent you from making this change. Now they do, because the server hello sent at first contains the TLS version, and it's cryptographically signed so the man in the middle can't change it. So the client can check to see what TLS version is being provided, and they will know. There's a single round-trip handshake. In the TLS 1.2, the client sends data and has to wait for a response, and then it sends more data and waits for a response. Remember, there are 3 handshakes, 3 back and forths to get the TCP connection, and then 4 more. Now they combined it into 1 round trip to save time. You don't have to wait for so many latency times. You can also do session resumption. You can reuse a pre-shared key from a previous session to make the new session resume. And so this is the resumption handshake. The client generates a key pair, goes up here, and the server replies. ORTT data is the session resumption data, which I'm somehow not seeing. Over here, there's ORTT data. Okay, it also sends that over. And the server can decide to just resume the previous session. How do they keep that safe? It's a good question, and I'm not sure we have any explanation of it here. No, it does look to me like a possible weakness. And in fact, I've heard of some attacks targeting this in various protocols. Yeah, why is resumption okay? Well, you do know you're talking to the right server. So I wonder. The other thing, I thought TLS 1.3 and even 1.2 had perfect forward secrecy, so it would never reuse a key. But apparently it can reuse keys under certain circumstances. So it's a good question, and I do not know the answer. This does look like a potential weak spot to attack. And it would be interesting to know more about what they've done to protect it. Anyway, the strong spots. It authenticates the server, typically only the server. You can, in principle, authenticate the client, but nobody does because then you have to pay for client certificates, although now I think you can get them free from Let's Encrypt. So maybe one of these days we'll all have client certificates on our devices, but most of us don't yet. Instead, we get the TLS after the handshake, then you send up something like a username, password, or a cookie. book mentioned that the nonce just counts upward as well. Yeah, I'm not sure. Anyway, so this does provide forward secrecy. If an attacker can steal a client's RAM, this would expose the keys and secrets for the current session, and it would expose old sessions that were still in RAM. And this is why something I've done several times is demonstrate when passwords are left in memory by browsers and such. Microsoft, since 2005, has provided this variable called secure string class, a variable that will be deleted when you stop using it. So a developer that is less than 20 years out of date ought to be able to code software that will not leave extra copies of old keys in RAM. But, of course, people won't think of that until they're caught doing the bad thing. Anyway, all right, so things that can go wrong, of course, if somebody was actually able to hack the certificate authority and steal all their stuff, then, of course, they would find all the secrets and they could impersonate the certificate authority and sell new certificates and everything. And this happened to DigiNotar, and at the time, the attacker claimed that they had also compromised 4 other major certificate authorities, although as far as I know, none of that ever was publicly disclosed, so maybe it wasn't true. And of course, the other problem is the certificate authorities are supposed to keep their private keys and never share them, and it is an open secret in the industry that they do share them with law enforcement, government, and anybody that bribes them with enough money. And this has been, over the last 10 years, this has been more and more obviously, blatantly put out there. Law enforcement, their devices sold to law enforcement to man-in-the-middle SSL. Now they're also sold to corporations, and you just have to feed in a thumb drive with a real root certificate. And TrustWave sold it. Many of the other certificate authorities have been selling their real root certificate for surveillance, so people are impersonating them, and that kind of ruins the trust of the whole system. This has been exposed very clearly over the last 10 years, and as far as I know, nobody has much of a solution. Various people have talked about having some kind of other measure of trust or some alternative like a blockchain kind of system for the root of trust and all that jazz, and all those have gone exactly nowhere. It's just become like many things, one of these things we all know is wrong, and we just got tired of worrying about it. But that's the thing. GoGo in Flight is issuing fake certificates when you connect. It's a fairly common thing for people to make things in the middle and issue fake certificates. Here's one that came out in 2008. Back then, VeriSign was issuing certificates that were using MD5 as the signature protocol. So they actually just forged an MD5 certificate, MD5, and duplicated one of their certificates with the same MD5. So that's what shamed them into stopping using MD5. Then they updated to SHA-1, and now, of course, everybody's had to update to SHA-2. All right. Then, of course, if the client is compromised, which would seem to be far more likely than the certificate authority, if you got malware on your laptop, and bad guys can read what's happening on your laptop, they can, of course, steal all your session keys or install a rogue certificate in the trusted chain, and if they have root on your machine, and there's nothing you can do to prevent that. There's nothing in the protocol to save you there. Heartbleed was a big one in 2014. Heartbleed was an unnecessary feature added to TLS where you could just request a echo of something just to make sure the server is still there. It was not necessary, but it was included in the protocol. But you would send it a letter, a word, to have that word repeated, but there was an unnecessary extra parameter in this request which specified the length of the word. And it never verified that the length matched the actual word. So you could send a short word and tell it it's long, and it would send you a long bunch of data, including your word and a bunch of random stuff from memory. So you could just pump random pages of memory out of the server by sending a lot of these requests. And usually what you'd find in there would be fragments of a page it had sent to a previous person. But if the server had just been rebooted recently, the real secrets were in RAM, like the private key. So this was really gruesome for HTTPS servers. And the main effect this had on the world was, of course, everybody had to upgrade their stuff to stop this. And it also caused all the people that had been going around saying Linux was safer than Windows, they got embarrassed and pretty much stopped saying that, because if you used Windows or Apple, this wouldn't happen. This was only open source stuff. And it really blew the lid off this belief that open source stuff was intrinsically more secure than Windows. I think the only thing that's fair to say now is that every system can be secure if it's set up skillfully by someone that knows what they're doing, and every system is unsecure if it's set up sloppily. It is not like one brand is safer than the other. You have whatever brand you use, you have to really understand how to set it up correctly. Anyway, so there's a test here, a free online test to test your TLS and see how good it is, or your browser, which is kind of fun. And there's Let's Encrypt, which is free certificates for everyone, which has worked out very well. I thought they would go broke or something, and they totally haven't. So that they were a large part of getting the whole world to start using TLS, and it's worked. Like I say, that's why you don't really need a VPN anymore, because everybody's pretty much using HTTPS, which is a fine thing. And HTTPS is better than it ever has been, but it never was perfect, and it's still not perfect. Here's a few other issues that are worth knowing. Strict transport security. There are ways to mark your website to make sure that people use TLS the best way. And this is one that tells you that you should only use HTTPS connections to go to my web page. I don't let any content load over HTTP, so your browser should know that. That's a nice one. Public key pinning is a thing that came and went. It was recommended that you should code your applications on like phones to know something about the public key, so that if somebody manages to impersonate a certificate authority and send you the wrong key, you will know. And this sounded like a great idea, but the problem is your certificates expire and the companies go broke and the companies merge, so you might have to move your certificate to a different provider. And if you do, how do you tell the people using your app to have the new certificate? Well, you'd have to update them, but people don't update their stuff all the time. So if it turns out that it creates a disaster for your tech support, and after recommending it for a few years, they deprecated it and said, you better quit doing it. This just turns out to not be a good idea. The increase in security is not worth the increased chaos in tech support. And so that was deprecated. Now they recommend using this new thing called Expect CT, which is a new header to prevent this, and I don't really know how it works, but this is the new hotness since 2017. But these are optional headers you put on your web server to try to prevent some of the flaws that might cause someone entrusting the wrong HTTPS certificate. Not that that is a common problem anyway. All right, and let me open up a Kahoot. You know, TLS is very good, and it always has been very good, but it's considered to be the most secure thing, and so people would like it to be perfect, and of course it isn't, so there's an endless chain of improvements. But almost all those attacks are very difficult, the exception being Heartbleed. Heartbleed made it easy to defeat TLS, and that's why people really got mad about it. I have access to this new theme. It doesn't appear to have changed the music. It doesn't seem to be a Christmas. Oh, there's a Christmas. This is a Christmas one? Doesn't seem particularly Christmassy to me. All right, anyway. Yeah, they've added some buzzy bass. I don't know. I haven't paid them any money, though. I can't really demand better service. All right, I guess this is it. All right, So what version should we be using? Right, none of these SSLs. They're all no good. You got to use TLS. All right, which message lists the possible ciphers? It's the client hello. All right. All right, which one mitigates traffic analysis? The padding, to prevent the size of the packets from changing. All right, what's the shortest secret key in TLS 1.3? $128. All right. And which of these is no good? Public key pinning. That's the idea that came and went. All right. All right. All right.